In this problem, we have a spherical balloon. So just picture any old balloon that you'd buy for like a party or something like that. And there's some child blowing it up. Okay. At a certain instant during the inflation, during the time that the kid's blowing it up, the air enters the balloon to make the volume increase. Now, whenever you're seeing an increase at a rate of, you're thinking some rate of change. So like here, we're looking at dV, the rate of change of volume with respect to time. So dV dt is going to be equal to 50 cubic centimeters per second. Okay, that's the change in volume with respect to time. At the same instant, the balloon has a radius of 10 centimeters. So at that exact moment when the child's blowing it up, the radius is 10 centimeters. The question is, how fast is the radius changing with respect to time? So here's what when you work problems like this, first you pull out what you know, any formulas that you might need. Okay, so for like this one, we're dealing with the volume of a sphere. So spherical balloon, we're dealing with volume. So we need to know that formula. So the formula for the volume of a sphere as a function of the radius, you don't need to put this in here, but it's nice to have. That's equal to 4/3 pi times the radius cubed, like that. So this is the volume formula, and we're going to be using this in a minute. The other things we know that the rate of change of volume with respect to time, specifically that we're looking at some time in question, we'll call it t sub naught, okay, that's equal to 50 cubic centimeters per 1 second. Okay, so we've got this. What we want to find, so you just basically make a list of things that you want, that you know, and that you want to know, and then you play around with the stuff until you find those. Okay, you set up your equations, you differentiate, so on and so forth. Okay, so at the same instant, the balloon has a radius of 10 centimeters. So the radius at time 0, as a function of the time 0, the radius is equal to 10 centimeters. We know that. Whoops, I'm sorry, I said we want. Hang on. We know this. Let me move this up. So we know that the radius at exactly time 0 is equal to 10 centimeters. Now the question says, how fast is the radius? What is the rate of change of the radius with respect to time? This is the guy we're looking for. So we have our equation that relates our volume to the radius. Okay, and they're both functions of time, right? The volume changes as time changes, and so does the radius. If you think about it, when the kid's blowing it up, not only is the volume, the amount of air in the balloon, changing, but so is the radius of the balloon. The radius of the balloon is increasing. Okay, so we've got this equation right here. So we know that v is a function of r. We know v is a function of t, and so is r is a function of t. So I'm just going to say, okay, v is equal to 4/3 pi r cubed. And what we want is to differentiate this. So using the chain rule. So we want the rate of change with respect to time of v, and v is a function of t, so we're going to use a chain rule here. And then this is going to be d dt of 4/3 pi r cubed. Well, pi is just a number, and so is 4/3. So I'm going to pull that out in just a minute. What I'm going to do here as well is I'm going to do my chain rule, and I'm going to say, okay, v is a function of time. So in order to differentiate this, I need dv dt. So here's my chain rule. d dv of v. So again, if you cancel these dv's, you end up with d over dt. We can't really do that, but it's a great way of thinking about it. So over here, I'll pull the 4/3 pi out, because that's just a number. And so this is going to be, I got to use, again, a chain rule, because r is a function of t. So this is going to be dr dt times d dr of r cubed. Okay, just like that. So dv dt, that's just a number, and actually we've got that right here. So we'll replace that in a minute. So this is going to be d dv of v is 1. So this left side just becomes dv dt. The right side becomes 4/3 pi times, now I'm going to rotate the order here, so d dr of r cubed is 3r squared, and then of course we have dr dt at the end of that guy. Again, we're just playing around with this. Okay, what we want to find, we want dr dt, we want this guy. So let's do a little bit of a simplifying here. This 3 and this 3 cancel. So what I've got is dv dt is equal to 4 pi r squared times dr dt. This is the guy I want to know, so let's solve for it. So dr dt should be equal to dv dt times 1 over 4 pi r squared, just like that. Now we can start filling the stuff in that we know. We know that the radius at time t naught, whatever that time is 10 centimeters. So we can put that guy right in here. So dr dt is equal to, we also know dv dt at that time, that's 50 cubic centimeters per 1 second. And so, what's dr dt? Now let's go ahead and fill this in. So this is 4 times pi times the radius is 10 centimeters, and we need to square that. So this gives me dr dt, the rate of change of the radius with respect to time. So how is the radius changing as time changes? So this is going to be, on the top is 50 centimeters cubed over 1 second times. So 4 times pi, this is going to be 100 centimeters cubed. So this is going to be 400 pi centimeters squared. All right. Okay. So let's just reduce this. So this implies that dr dt is equal to 50 divided by 400 is 1 over 8. So this would be 1 centimeter cubed over 8 pi centimeters squared. So 2 of the centimeters cancel out, and I'm left with 1 over 8 pi centimeters per, I lost my second down here at the bottom, per second. The second right here should be down here as well. I'm not going to write it in there. So we end up with 1 over 8 pi centimeters per second, which if we go ahead and we do that number out, that gives us approximately 0.04 centimeters per 1 second. So at that time, big picture is, at that time when I can only draw this in 2 dimensions because I'm really bad at drawing 3 dimensions, guys. So if we have a balloon, okay, and its volume is increasing by 50 cubic centimeters per second, the amount that the radius changes, so as the volume changes, the sphere gets bigger. Okay, so big picture here. The distance, this little guy right here, that the radius changes, so if the volume increases by 50 cubic centimeters per second, then the radius, this guy, changes by 0.04 centimeters in that 1 second, roughly. I mean, this is an instantaneous rate of change, so it doesn't increase that same over that whole second, but it gives you an idea. So we're increasing our radius. A good approximation is our radius is going to go to 10.04 centimeters in that 1 second that the volume increases by 50 cubic centimeters per that second.